Welcome to Intro to Backend Development, Lecture 4. Today we'll be covering abstractions, so how we can abstract our code and our file structure to be more efficient and make our code more readable and developer-friendly. But first, a review on what we've covered so far. So in the past two lectures, we've been dealing with servers accessing databases by communicating via SQL, the structured query language. Servers communicate with the database by using SQL commands, whether they're queries to retrieve, create, update, or destroy information. And in response to a SQL command, a database will return any relevant data that's associated with that operation. Last time we covered relationships, which is how we create relate data to other data in a structured manner across different tables or even within the same table. We do this through what are called foreign key columns, and these foreign keys basically represent IDs of one table being present in another. And the three main kinds of relationships we discussed are one-to-one, one-to-many, and many-to-many. First, an example of a one-to-one relationship, we gave users and profiles. So as you can see, a user, John, ID 10, has one and only one row corresponding to him in the profile table, referencing him with the foreign key column user ID. And similarly, every profile table has one and only one reference to the user ID, in this case, number 20 referencing Jane. An example of a one-to-many relationship is like albums and songs if you're making a streaming service, for example. So you could have albums with single ID, but they can reference multiple songs in the song table. And conversely, each song in the song table can reference one and only one album. So creating that distinction of one song, many songs to one album to many songs. Then we covered many-to-many. We covered some couple naive implementations of a many-to-many relationship and ultimately showed you the common approach, which is to use what's called the join table, also known as an association table. In this case of students and courses, we're trying to remodel somewhat of like a CMS-like system. So in the case of students and courses, every student table every student in the student table has an ID, and you can find the relevant courses associated with it on this join table. In this case, we have student ID to course ID pairings. So then once you collect the course IDs corresponding with that student ID, you can find these courses in their appropriate table. And conversely, you can traverse the reverse direction. So courses discovering all of their students, you go to the same join table, look at whatever student IDs are associated with this course ID, and then you can gather whatever student information you'd like. And then for updating student-course relationships to this application, it's as simple as adding new rows to the join table. So today we'll be covering more about the SQL drawbacks and why we don't want to write raw SQL commands in our Python code, and how we want to use abstractions to get away from the down and dirty with SQL. But first, some pain points to identify are, first, lower code readability. This is really huge as you expand on the complexity of an application, and especially if you're having multiple developers working on a project. Having readable code not just for yourself but your teammates is crucial to ensure speedy development and not making future mistakes. Next thing we'll talk about is being susceptible to vulnerabilities. SQL has some semantic things that are exploitable for experts who understand how applications are designed and can take advantage of databases, and this is like a common cause of when we have breaches and unauthorized access of data, is because SQL itself has some vulnerabilities, that are like come up because people are poorly designing their applications sometimes. And then we'll also talk about some runtime exceptions are generally not handled well with SQL. As you saw in like our previous demos and assignments, we like to wrap the create table methods and try excepts just to avoid the issues of accidentally creating tables that already exist, because SQL will automatically just throw a fat exception and crash the whole application otherwise. So we have to manually involve Python to handle a lot of these exceptions for us to make sure that our application can still run smoothly. All right, first, with readability, this is a comical example, but this query you see below actually is from a real assignment in Cornell's database course. And actually, the query goes on for another 3 or 4 lines below what you can see right now. But this is just trying to highlight the fact that when you have a more complex application with many tables at play, and you're trying to do complex queries, things can get real messy real quick. As we showed previously in the demo and lecture, we can do a thing called what's a join query. This is mainly used for when we do like relational databases and you want to query over multiple tables, how you have to get like nested selects and nested table creations going on. And this is kind of like an example of what that can look like. It's not pretty, and we want to avoid this as much as possible, but we still want to be able to have these complex queries, so we need to do something other than just raw SQL to achieve that. Next on vulnerabilities, the main one we'll talk about is something called SQL injection. This is a malicious user being able to specially craft some kind of input to an application to trick the SQL semantics if they understand on a deeper level what's actually happening in the application's authentication scheme. And this can allow database access to people that shouldn't have access to things. So being able to query data or corrupt or even delete existing data are all vulnerabilities that are exposed when we use just raw SQL implementations. To show an example of this, we'll show how you can break a login scheme. So consider just a regular example of an email password logging into some random application. We'll use the cache email and cache password variables to represent whatever user input may come in. But you can imagine we would have a SQL query like this to give back the user information associated with someone trying to log in. So select everything from the user table where the email is this specific email input and password is equal to this specific password input. So just following through with like an example, if ABC123 was trying to log in and the password's backend, this is what like the SQL command would look like. And so if we can imagine what's going on in the query as we're traversing our user table, we would say maybe encounter like many rows where the email is not equal to ABC123 and the password is not equal to backend. So you would have where false and false. Maybe eventually if the password is wrong, but you found the right email, it would say email is true, but the password is incorrect, and that would give you nothing back. But finally, if you got the right password and email combination, both would be true, and then you would be returned back the user information associated with this unique email password pairing. So now back to the general case of random email and random password coming in. What this could look like from a malicious user trying to do SQL injection is inputting a password like this. So some random input, and then here we have like an apostrophe or 1=1, semicolon, and then dash dash bracket. And if we were to input this string directly into our SQL query, like someone might want to do if they're implementing this application, you can read at the bottom, we now have select everything from user where email equals email, doesn't matter really what it is, and password equals some string, or 1=1, colon, and then this random stuff after that semicolon, that's actually shorthand for like SQL comments. So just like you can use the hashtag symbol in Python or 2 backslashes in JavaScript to comment out code, the dash dash bracket can be used as a comment in SQL to just ignore everything after that command. And then once we drop that semicolon there, it just cuts the query short. So now we can imagine how we would play through this actual query being made. You can see email equals email. That's probably going to be false for a lot of things, especially if it's dummy data. And similarly, password equals XXX, also likely to be false. But 1=1 is going to evaluate to true because 1 does equal 1. So we can imagine the query would then look like this in an abstract sense, and as it's being compiled. And then SQL will go through false and false will evaluate to false. So now we're left with select everything from user where false or true, but false or true will evaluate to true. So now suddenly we have a very scary query for anyone to write actually, where select everything from user where true, which will essentially give back all of the information in the user table completely, and thus giving this malicious user complete like access to the database and seeing all the information present in this very precious user table. As you can see, this is a big problem. This, of course, is a kind of like dumbed down explanation. Hopefully people would do some cleaning or things before actually just throwing in whatever user input directly into a SQL query. But this is kind of like the motivation of like the vulnerabilities aspect of SQL and why we want to use some other schemes to prevent this. So the main abstraction we'll be talking about today and showing later in demo is called an object relational mapping. The basic gist with an object relational mapping, also called an ORM, is thinking of objects as like rows in a database. So you query and manipulate data using objects rather than thinking of things being more in tables. So you still preserve like the database using SQL for like all the storage and query benefits, but in actual like code, we can reason about entries as instances of an object is like a more object-oriented approach to programming using like classes. So an example, and we'll see it show later, but from an abstract sense, like what we would see SQL versus like an ORM implementation of a user, you would see SQL would just go right at like you would manually write out creating your user table like we did for the past 2 assignments, while for an ORM it would just be like defining a class and then indicating some column fields with another custom class provided by the ORM package. So you would still have the ID, name, and age columns, and this ORM code would eventually boil down into the same SQL code we would use, but in terms of the developer experience, it's a lot cleaner and easier to reason about what's going on in the code versus writing raw SQL. So the code ORM that we'll be using is called SQL Alchemy. It's a popular ORM for Python, and it comes in with a lot of built-in goodies for us to use. We won't go through all of them, but we encourage you, and we'll link you the resources and documentation to read more about it if you'd like. And it also integrates really well with Flask. The two are used very often out in industry for people making quick applications or for side hobbyists just wanting to build things, and it's why we like to use it in the course. So the benefits of an ORM, first off, readable code that more closely resembles how we reason about code in general. OOP is one of like the most common coding approaches, styling used ever. It's taught a lot in other classes at Cornell, and it's used heavily in industry. So being able to make it easier for the developers to understand what's going on in the code will make them faster and better developers for whatever application they're building. This abstract SQL-free representation also frees us to think, it makes it easier, it makes it faster, and also make sure that the database and application use the same logic base. So as you saw with the previous examples, when we're using the SQLite 3 package, we can use the self.con.execute method to manually input SQL queries, but it's really not great for a developer to have to know all of the intricacies of both Python and SQL if they're going to be building an application. By having everything in one language, in our case we'll be using Python, it makes it easier for the developers to keep things consistent across multiple files and multiple parts of the application. This also gives us greater cross-compatibility with databases. SQLite is just one database management system. There are other popular ones like Postgres or MySQL, and many ORMs allow you to link up to different database management systems, which can have their own pros and cons, but basically give you more freedom and modularity to go along with your code. And of course, this also helps us secure against SQL vulnerabilities, main one being injection, because many ORMs are open sourced or developed by more competent individuals than ourselves, and so they account for these things when they design the ORM to handle querying to make sure that it's cleaning for injections. On the other hand, there are some drawbacks within an ORM. So namely, there's slower query performance, especially in complex queries in general, because there's more application code. Your server, your computer has to compile higher level languages like Python, eventually down to lower and lower levels like C or even SQL to actually execute all of these operations. So there's some lag time there. But for more complex things, mainly traversing many-to-many relationships and going over multiple tables, ORMs aren't as efficient at bringing a large query and compiling it into one thing, but rather it may take multiple queries to get the same information that a raw SQL expert could just do in one query and be a lot faster. For our purposes, it doesn't matter if we're milliseconds faster, but in the context of maybe stock trading algorithms or things that where time and milliseconds matter, ORMs are not really recommended. Also, this may abstract away the fundamentals of SQL. It's part of the reason we don't dive straight into ORMs in this course is because we want to make sure that people who are learning this for the first time actually know what's going on in the background when they're writing their code. And ORMs are a superior developer experience, and it's because they're very popular as well. So it's key to make sure that people are learning the fundamentals of backend development and understand actually how their application's working when they're writing code. The next abstraction we'll talk about and also show later in the demo is called a data access object, also called a DAO. So the overview of a DAO is just an abstract interface of working with your database. So before, we may have like custom methods in the database driver class we had for assignments 2 and 3, where we would have like get user by ID or like get all users. It's basically recreating that, but to link up with like the ORM. So it's an additional layer that sits between like your application code, being mainly like the file with all the routes, so our app.py that interfaces with clients. And so it sits between like that and what we would call like our database interface, so like a db.py, which is where the ORM will reside. And so it gives us specific data operations without exposing any of the database details. So just having another layer in between the two gives us more modularity to switch out and update various parts of the code without impacting or influencing the other, because this interface exists in between them. And also allows us to write cleaner code, because if we're making the same types of data operations, it makes sense to have methods designed just for that purpose to be called on the application side to make things cleaner from a development perspective. So here's like a more graphical example of what we mean by placing a DAO as an interface between the application and the database. So imagine you have an external source coming in, like a client requesting some information. It interfaces with the application, hits a route or whatever, appropriate logic. Then it interfaces with the database, retrieves with a SQL command. In the case of an ORM, it'll like do some ORM query, which will then boil down to SQL to interact with the database, send that back up to the application, and eventually back to whatever source is requesting and interacting with our application side. So in the case of the DAO, it'll sit in between. So our new flow, external source will still operate with and interact with the application, but now the application will go through the DAO to retrieve whatever resources it's needed or whatever operations it needs to do on the database. So then the DAO will interact with whatever database implementation we have, do its deal, come back up through the DAO, and return whatever necessary information to the application, which can then go back out to the external source. So the main benefits of a DAO and why we use it in development is to separate what's called like the business and database logic. Business being the side that's interacting with clients. So mainly in our case, like where all of our routes are located. And the database logic being where we actually define our database schema and other attributes surrounding like our table setup. This also allows for safer and smoother development. Safer in the sense that we protect ourselves from maybe like making a change in db.py that may affect how it's being used in app.py. If we have the DAO in between the two, that kind of abstracts the use of the database. One change is less likely to impact the other, as long as like specifications and function invariants are still like held consistent. And this in turn makes for a smoother development. It's easier for developers on multi-person teams to go through and change one part without affecting the other part of a code. In development, and you'll learn this language in later classes, this may be called like modularity, or more commonly like orthogonal or orthonormality, just basically separating different parts of code that have different purposes. And this ultimately like makes our code cleaner and easier to read for us as well. Some drawbacks of using a DAO: leak abstraction. Maybe if you abstract too hard, or if you're abstracting not in like the correct manner, you may have like when you think you're abstracting, you're actually still showing how the database is operating underneath, which is like kind of avoiding the purpose of the DAO. Another thing is like code duplication. So using a DAO actually may involve writing more lines of code physically, because like you're defining all of these new methods and such and new files. But yes, that's another thing to consider. And also may hide the cost of database operations. So like from the application side, calling an ORM method, and maybe it needs to like spam it, say in like a for loop in some case, that'll like cost a lot of database operations, versus if the application knew how everything was working on the database side, it could jumble everything into maybe one query to use on the database to accomplish the same effect. But now, because we have this layer in between and have separated those like two from knowing how each other work, we have like the possibility of having more hidden costs associated with the application. But once again, this isn't really a consideration for this course. If you want to learn more about optimizations, we recommend trying learning this through internships or future courses like databases. And that's all we have to talk about right now about abstractions. So just to review, we talked about ORMs, object relational mappings, and how we can define table schemas and define our database with by abstracting it, still staying in Python code, and reason through entries in a database as objects in like a class-based system. And then the second abstraction being data access objects, the DAO, to separate how application code and database code interact and make sure that we're writing clean and easy to read and work on code for us. Yeah, thank you, and we look forward to seeing you in the demo.